Welcome to the SEI Podcast Series, a production of the Carnegie Mellon University Software Engineering Institute. The SEI is a federally funded research and development center sponsored by the U.S. Department of Defense. A transcript of today's podcast is posted on the SEI website at sei.cmu.edu/podcasts.
Welcome to the SEI Podcast Series. My name is Suzanne Miller, and I'm a principal researcher in the SEI Software Solutions Division. Today, I am joined by the director of the SEI, Dr. Paul Nielsen. We are here to talk about the growing need for the disciplines of systems engineering and software engineering to develop effective ways of collaborating, especially in the era of what we call smart systems. Welcome, Paul.
Hi, Suze. How are you doing today?
Good. Glad to be here talking with you.
Yeah.
So let's start out by you telling us a little bit about yourself, because not everybody knows you, and why, as the director of a software federally funded research and development center, you feel it's important to be discussing the systems and software engineering collaboration in relation to smart systems.
Sure. Okay, Sue. So first of all, I've been here at the Software Engineering Institute for about 17 years now. And, we're an FFRDC that concentrates on software engineering, cybersecurity, and AI engineering. But before I joined here, I was in the Air Force for 32 years, mostly working on space systems, command and control systems, and science and technology. In my job in the Air Force, I was really more of a system engineer most of the time, although I'm trained as a physicist. And now, of course, here I am in a Software Engineering Institute. And it just struck me from the very beginning of arriving at SEI how these two disciplines of software engineering and system engineering sort of had grown apart and yet had so much in common and could really benefit from learning from each other. So one of my own sort of personal initiatives while at SEI has been to try to bring those two disciplines closer together.
And I know this is not a new issue. When I joined the SEI in 1993, one of our first activities was actually helping to formulate some guidance on systems engineering in relation to software. And so this is something that, as you say, it sort of waxes and wanes in terms of interest and importance. But we're now moving into kind of a new era, I think, that we want to talk about. Which is the smart systems. And so let's talk about that trend towards smart systems and how that kind of leads to this convergence of systems and software engineering.
Sure. Well, as we move into this era where we have more aspects of artificial intelligence in our systems, it becomes even more important that we architect and engineer these systems well. In most cases, these systems end up being more complex and more interconnected than systems were in the past. And the whole movement to this larger type systems and interconnectedness really is one of the rationales for why system engineering and software engineering got started. Because at some point, you have to break the system down into modules or components or subsystems, as system engineers would say, and then build them back up. And so both of these disciplines have done this in the past in various ways, but now we're seeing that the systems we're building now are never all hardware or all software. They're software and hardware systems. Sometimes, as you know, we call those cyber-physical systems. And in addition, sometimes now, many of our systems also have aspects of social merit in them. So they become socio-technical systems as well, which even adds another level of complexity.
These are words with lots of syllables, but that's because, the cyber-physical socio-technical systems, that describes a wide range of aspects. And I would argue that that's actually one of the key reasons that systems engineering and software engineering need to collaborate, because that cyber part is software, that physical part, systems engineering has traditionally dominated. And then you get into the socio-technical, and both disciplines have to deal with that social aspect.
That's right.
And it's so working together makes perfect sense in this kind of world. What are some of the opportunities?
Well,
Sorry, go ahead.
One thing, Suze, is that if you go in the past, as always, life was simpler in many of our views, and engineers worried about engineering things.
Yeah.
But now we find that that's not enough. Whether we're worried about equity or climate change or regulation or fairness, all these extra things come in. And so we're finding that as engineers, to do our job right, we have to consider them as well.
So, what are some of the opportunities that may be different from the past of achieving synergy between systems and software engineering that you see?
Well, I think there's lots of them, obviously. One of the key things for any discipline is that it usually brings some ways of looking at problems, examining problems, and tools. And different disciplines always have some different tools and some different views. When you get to systems that are highly complex, man, as an engineer, you need all those tools you can bring to the table. And so by bringing these two systems together, we bring more tools to the table that allows people to solve kind of hard problems. In addition, just as we always talk about diversity and inclusivity, when we bring people that are trained as software engineers together with people that are trained as system engineers, we get the best of those worlds together too. And as you know, many of our systems today, a lot of the functionality rests in the software.
Right.
That we have physical parts of the system too, but a lot of the functionality rests in software. So we need those different views to make these systems work.
And I would argue that systems engineers and software engineers, in my experience, visualize the systems differently.
Yes.
And that difference is one of the things that we need to leverage.
Yes.
Because when I have software engineers that are all about the data and where the data is coming from and where it's going, and the hardware is often the transport vehicle for that data, that's a different view of the world than a hardware view of the world, which is this component fits inside of that component, fits inside of that subsystem. So being able to marry and get advantage from both of those views, which are a little bit orthogonal, can really influence things like your architecture, right? We want evolvable architectures. And hardware is harder to evolve in some ways than software, although we can make software difficult to evolve too.
Yes, we can.
But having that viewpoint of I want something evolvable is one of the ways that we start taking advantage of each other's disciplines in what I see.
Yeah, and I think evolvability is maybe one of the key, we would call it a quality attribute in the software engineering world. Maybe the system engineers would call it a non-functional requirement. We're finding that one of the best ways to make really good systems is to keep evolving them, to keep improving them, not to have a static endpoint and push them out the door and never to be changed again. That's also a real hallmark of something that was developed in the commercial software world of DevOps and continuous development, integration, and delivery and deployment. And that's a little more stressful for the physical side of things, for the hardware side. But in software, the commercial companies have brought this almost to the limit of upgrades many, many times a day. Like I said, a little tougher on the hardware side. But I think the hardware side is trying to learn from the software side in doing this continuous evolution in a different way than they've done in the past.
So that relates to one of the government initiatives that has taken root in the last few years, which is digital engineering. And the idea that as part of sort of solving that problem of making the hardware more evolvable, we do more of our analysis and real engineering of what are our options and which ones should we close out now and which ones should we experiment with more in modeling environments. And we're actually starting to talk about mod DevOps, right? We've got, modeling dev and ops together. Is that one of the places that you're seeing some of this opportunity for kind of bringing the engineers together? Because the systems engineers tend to be very comfortable with these kinds of modeling techniques.
Yeah.
And they need, they can help us to understand some of the perspectives that way.
Sure. And both disciplines had really jumped into the model-based design and analysis kind of field. What we're finding is that the ways both disciplines were doing this were very compatible. And through model-based design, you can iterate design much earlier, you can look at alternatives, you can examine not only the quality of the system you're going to build, but in some cases you can get quantifiable results too for all kinds of things like performance and throughput and latency and such. These can be very important in a system sense. And so in the software engineering world, the DevOps initiative is one thing, but then the model-based software engineering is another.
Mm-hmm.
Right now, we're looking at ways to bring both of those to bear on the very complex problems that we're seeing.
And I want to, we've done podcasts on model-based engineering before. I want to remind our audience, when we talk about model-based engineering, we're not just talking about model-based specification. We're not just talking about representing just the requirements in a model. We're talking about using that model to analyze effects of making changes, effects of switching out components, effects of changing architectures. And that's when we really get the power of the model-based engineering into play, which I think our systems engineering brethren are very excited about.
Well, in some ways, these models can have enough fidelity that they can actually lead to self-generating code ultimately. And so they're almost like a higher level language in a way. These models can be that good that they're a higher level language.
What are some other developments that indicate progress to the convergence of these disciplines that we've been talking about? We've talked about model-based engineering. What are some other indicators for you that that we're getting farther along with this?
Well, one of the most basic ones is that both communities seemed like they wanted to talk, which is a good start, right?
Yep.
And just like you can have people who speak two different languages, we early on found we had different languages for certain things. Sometimes we were talking about the same thing, but using different words. And so we had to come together and start to understand each other's vocabulary and such. One thing that's been very encouraging to me is that the Professional Society for System Engineers in the country, in COSE, the International Council of System Engineers, has been reaching out to us for some time to try to bring this marriage of software engineering and system engineering together. About 4 years ago, they started an initiative where they established a working group to look at these interfaces. Mm-hmm. And of course, we had several people working on that, especially Sarah Sheard, that worked on that quite a bit. But then, even more recently than that, they're doing a big, this society in COSE is doing a Vision 35. What is system engineering going to be like in 2035? And I've been working on that document with them, and it has lots of aspects of how system engineering and software engineering have to work together. And I think it's a growing awareness of the strong amount of content and functionality that resides in software. It's not enough just to balance the hardware part of the system now. You have to have everything balanced. And system engineers for years have done this allocation of requirements, allocation of functionality. And at times that was to hardware subsystems, but now they're realizing that the software itself is bigger than any subsystem, so they have to look upon it as a more major constituent of the system itself.
And it's cross-cutting.
Yes.
I mean, that's one of the things we talk about in some of our classes is that kind of the mental model of hardware engineering is this is a part of that.
Right.
The mental model of software is this and this and this and this, use that.
Right.
So it's not the same, it's not a structural view, it's more of a usage view. And that alone, creates a different way of looking at the two systems. And when we can I know in my case, when I've been able to get the systems engineers and the software engineers to talk about that, we get a much richer conversation about how do we deal with some of the software architecture issues that you're only going to see in this one subsystem. But if you don't solve them there, it's going to affect everybody that uses that element of the software and that component of the hardware.
That's right.
So there's a lot. I mean, this is obviously, you and I share this passion of trying to help these two communities come together. What effect do you think that the work we've done in the National Software Agenda has on that? Because I see some places in that agenda that, immediately say, hey, this is something we need to talk to the systems engineering community about. Has that played into the sort of Vision 2035 and things like that?
Yeah, it's really helped inform me a little bit as a participant in the Vision 35 work, because I've tried to stay close to all the work we were doing on the National Agenda for Software Research and Development. And that was an effort to sort of look 5 to 10 years out at what's coming in software so that we can be prepared to help DoD and our other customers and clients. One of our jobs as an FFRDC is not only to solve the problems that people are seeing today, but also to get ahead of the problems that are going to come in 5 to 10 years. And there, as you alluded to early in this conversation, this move to smarter and smarter systems just keeps coming up. Sometimes I think people think we're either going to have an AI system or a non-AI system. But in fact, AI and ML, machine learning, are creeping into the systems throughout. Lots of times, like our cars, it's not like we're going to have a self-driving car right away, but we already have AI elements in our cars today, that help us with making sure we don't go out of our lanes, that help us maybe park our cars.
Yes, that annoying beep.
One thing that I need because I one time was in a hurry and backed into my garage door because I forgot to put my garage door up. And now they have things that keep you from doing that. They'll keep you from backing into your garage door. Very helpful for some of them.
And save you some money too.
Yeah. And so what we're seeing all along is the introduction of elements of AI into our lives. A lot of people right now say, oh, well, I'm afraid of AI, but they use AI every day. Every time they go onto Google, every time they shop at Amazon, every time they get in their car, they're using elements of AI in their daily lives.
So I taught AI as a course in 1989.
Yes.
And in that time frame, it was a very limited view as to what we could do with AI and the
yes,
just the compute power. I mean, all kinds of limitations. Even though the concept, people could get the concept, the implementation was really, really challenging. And that's that shift to where neural networks and the computing, parallel computing, and other things in the computing industry that have made the implementation of AI and ML possible. That's another area where I think there's a place for systems engineering to learn more about what can you really do with this? Because
yes,
in many of the systems that we work in, the systems engineers have built systems like this, these cyber physical systems in the past, but without that extra boost that you can get from some of the AI ML technologies. And so that's another opportunity for learning is where can you really leverage that?
Mhm.
And because we have a cyber component, how can you leverage it safely
Right.
and securely so that you don't end up creating vulnerabilities in the way that the software is interacting with the hardware? That's actually one of the vulnerability points that we have to watch
Sure.
for. So this is, I see lots and lots of opportunities for this. And I think the focus on, we now have a new directorate on AI and ML, that getting these communities to understand some of that future is going to be one of the key things that we can contribute and that you can contribute in things like the Vision 2035 effort to sort of ensure that doesn't get lost.
One of the things that actually is challenging and changing both system engineering and software engineering is AI engineering with its strong dependence on data. So now data almost becomes the preeminent thing. The data that you use to train the systems, the data that you use to evolve the systems. And learning how to make a good data set for training is going to be a new skill. How do you make sure the data spans the dimensions of the study of the problem you're trying to solve? How do you make sure the data doesn't have intentional or unintentional bias in it that would lead you to the wrong answers in certain conditions?
So I would say that's one of the things that we'll be doing in the future to help these engineering disciplines is to help understand the impact of data, the impact of hardware software interfaces
Right.
to remove and reduce vulnerability. What else do you see this SEI doing in the future to help these two disciplines keep pace with the rapidity of technological change? I mean, we're not just talking AI ML, we're talking quantum computing, biological, cellular computing. There's a lot of stuff on the horizon. What are we going to be doing for that?
Well, I think the work that's kind of been ongoing with DevOps, which leads to smaller incremental changes, but very rapidly, helps tame this exponential growth in science and technology that keeps coming. It gives us a better chance. Because in the past, when you tried to plan maybe for a system 5 or 10 years out, it's very hard to do that planning in a world that changes so fast. But when you're bring that down to the level of a sprint that we might say in the agile world, or a quick development cycle in the DevOps world, and you're talking now of a week, 2 weeks, maybe a month or so, it's much easier to sort of tame the future because you can see that far. So I think one of the things that we can bring to the table is this ability to live in a world that's changing very fast by bringing our vision near term and taking advantage of what we know, even as we plan for future evolution in the future cycles. I think that's really a hallmark. And anything that exponentiates, whether it's interest in your bank account or software capabilities, it's very important not to start from scratch each time, but rather to build upon the past. If you can keep building upon the past, you can achieve so much, as we've seen.
And that kind of leads into one of the other areas that we emphasize is how does in the DoD space, how does all of this affect the acquisition life cycle
Yeah.
and the people that are doing the purchasing and buying of systems like this that have traditionally been very, very long periods
Yeah.
of time.
I've spent my life in that,
We
Susan.
may have the technical capability of doing quick turnaround, but can't, we've got to also learn to affect that acquisition cycle so that it can accept change in a very rapid,
Right.
kind of cadence. And that's one of the areas that I've worked in, and
Me
I see
too.
a big change in that over the last 10 years.
Well, yeah.
But it takes a long time to change the social aspect of the system.
Well, we've certainly seen a lot of interest in that. And, over the last few administrations, we've seen people on both sides of the aisle pushing to reduce cycle time, to open up the experimental window, prototype window, to bring modern software engineering techniques into the fray. And I think what they're finding is that, it's harder to accelerate the hardware cycle than it is to accelerate the software cycle. So one of the things to do is to build hardware platforms that can accept good software changes so that you can upgrade the capabilities of the system fast. Now, in the commercial world, we see that in some of the software primary systems like Netflix and Google and such. They've done a real good job of that. But we also started to see that in some of the hardware-intensive systems like a Tesla car, where they can do upgrades overnight in the car. The Air Force, kind of following Tesla's lead a little bit, recently updated software on aircraft in flight, while it's in flight, not when it's on the ground getting its maintenance role, but in flight, gave it a new software load. I think we're going to see more of that, to build platforms, that have certain physical capabilities, but where we can change the software much quicker so that we can continue to bring new capabilities to the soldiers, sailors, airmen, Marines, and now we have to say guardians too.
Yes, Space Force.
Yes.
I want to thank you so much for talking with us today. I always enjoy these conversations with you, and this topic, when it was brought up, it's like, oh yeah, I want to do this one. Because I think, like I said, you and I have this passion for looking at these interfaces between these communities and trying to make systems engineering and software engineering more effective together is what's going to get us the capabilities for quick turnaround and for things like, scary enough, software update in flight. That's one of the things we've been talking about for decades. And it's like, oh my gosh, it's finally happening. But, that's part of the world we live in, is how do we do these things? And I really appreciate your insights. I appreciate very much your work with the Vision 35 group, because being represented there at that table is actually one of the things that is a sign to me that we're really getting much more synergy between our disciplines. So I look forward to the work that comes out of that.
Well, I'm excited about the future. I think engineers should all be excited about the future. When you bring different disciplines together, that's usually a time of really fertile innovation. I think we're getting to that point where we can do that. And I want to thank you for this nice interview, Susie, and take care of yourself, okay?
Absolutely. We all have to take care of each other right now. I do want to make sure our viewers know that we'll include links in the transcripts to things like the Vision 35 project and other things that we've mentioned, model-based engineering and such. So they'll be able to see that transcript. I want to thank you, and I want to thank our viewers for joining us. I think everyone's going to enjoy this podcast when it comes out, and we're going to go off and create the future.
You bet. That's what we do. That's what engineers do.
Thanks for joining us. This episode is available where you download podcasts, including SoundCloud, Stitcher, TuneIn Radio, Google Podcasts, and Apple Podcasts. It is also available on the SEI website at sei.cmu.edu/podcasts and the SEI's YouTube channel. This copyrighted work is made available through the Software Engineering Institute, a federally funded research and development center sponsored by the U.S. Department of Defense. For more information about the SEI and this work, please visit www.sei.cmu.edu. As always, if you have any questions, please don't hesitate to email us at info@sei.cmu.edu. Thank you.